So thank you very much, firstly, to the organisers for organising this great conference and for giving me the opportunity to talk about the work that we've been doing. I'm going to talk about a cluster at redshift 2 and what we've learned about the cluster's ICM since the last galaxy cluster formation meeting. I'm Rose, I'm a postdoc in MPE, and this work has been done with all of these wonderful collaborators. So I think we've already had a very nice introduction into the general interest and importance of understanding the heating of the ICM. It's a very active topic. So I think I'll just say that we see at low redshift this very clear interaction between AGN radio jets and the ICM. We see these cavities in the X-ray. And I think that picture is less clear at high redshift, although we're seeing some nice examples of it today. I think we really want to understand what a quite typical scenario is at redshift 2, not just the most extreme objects, and how that might differ from low redshift. So that's our real motivation for doing this work. So this is our cluster, ClJ1449, is at redshift 2, so it's fairly high redshift. And it has a very varied galaxy population. So we have these red galaxies in the core that are already forming a red sequence, they're quenched. And we also have these much bluer galaxies and these very highly dust obscured galaxies. So they're star forming. So it's a really mixed bunch. We've already detected the cluster in the X-ray in these gray contours. And because of that, we know the mass, and that is going to be a typical coma-like cluster by redshift 0. So for what I'm going to talk about today, we're mainly using submillimeter and radio observations, and we have a nice set of those from ALMA and VLA. And I'll quickly summarize what we know about the galaxies. So through their CO observations, we know that they have very highly excited molecular gas compared to field galaxies at this redshift. We know that they have high star formation efficiencies compared to field galaxies, the Kennicutt-Schmidt relation. And when we look at the galaxies, we see that there is a really high fraction of galaxies that are merging, interacting, or at AGN. So this is really just to say that this is an opportunity to study the ICM in a cluster that is very active still. It's a very active stage of its evolution. So how to study the ICM? We've talked about some really nice Ssaid surveys looking at local galaxy clusters, but as Rebecca said this morning, it's essentially redshift independent. So it's also a really good tool for looking at our cluster at redshift 2. So in order to get an independent measurement of the cluster total mass, as well as perhaps some first constraints on the energy injection from AGN or star formation, we looked at the Ssaid emission. So we're working at 92 gigahertz here. So we're looking essentially for a negative flux, an Ssaid decrement. And we've seen that we have lots of highly star-forming galaxies in the cluster. And these are going to be emitting positively in the submillimeter and filling up that decrement, making the Ssaid impossible to detect. So our first step is to get rid of this positive flux. So to do that, we use ALMA observations, where we can identify individual galaxies, including interlopers, and we measure the fluxes at 92 gigahertz, which can then be subtracted in the UV plane, both from the ALMA data itself, giving this image. And then we can also do the same thing using the ALMA measurements from the ACA data. This is a much lower resolution. It's much better for looking at the Ssaid, but it's not any good for trying to subtract the galaxy emission. And this is what we have here. So this is what we find. And when we combine our ALMA and ACA data, we have this really nice 5 sigma detection of the Ssaid feature in this relatively low cluster. We see it here in the yellow contours next to the X-ray. And we can see that there's an offset of perhaps 50 kiloparsecs between the center of the Ssaid emission and the X-ray, and also offset with this cluster of galaxies here, this set of interacting galaxies, that is the future BCG. And that's also shown in this figure here. It's not completely unexpected to have this sort of offset for a galaxy cluster that is perhaps not completely relaxed or is at quite high redshift, but also it's such a small offset that it could just be an effect of the noise. But this is our Ssaid detection. So to try and get some physics out of this, we look at the profile, flux as a function of the spatial scale. And that's shown with the white points here. We fit to that several different models for the pressure profile. So with and without AGN activity, for example, and also with or without a cool core. There's a couple of examples of that shown here. Based on our data, we don't really find much of a difference between the pressure profiles. So we don't get strong physical constraints on which of these might be a better fit, with the exception of perhaps one of the AGN feedback models that seems to give quite a different mass to the rest of the models. All of the other profiles are in agreement with the Chandra constraints on the total mass, so that's really nice. We also see evidence for perhaps a lack of power at small spatial scales. That's this kind of flattening of the pressure profile here. And it's possible that this could be due to some positive emission that we missed in the subtraction. So perhaps galaxies that are very faint, they're below our detection threshold, there's nothing we could do. Or perhaps it's from diffuse cluster ICL, the intra-cluster light that might contain some dust. But if it is physical, it implies that there's a lower electron density or a lower temperature than these profiles. And that might be caused by, for example, AGN-generated cavities. Having said that, of course, we can't see whether our AGN profiles fit better than our non-AGN profiles. And also the profiles themselves are often calibrated at low redshift, and there might be a bit of a difference between what we'd expect at low redshift and high redshift. But I thought it was an interesting point to pick up on. And if we want to carry on thinking about AGN jet-induced feedback into the cluster, then the natural thing to do is to go to the radio emission. So this work is led by Boris Kalita, who has just given the previous talk and has given a bit of a spoiler alert as to the end of this story. And this is our 3 gigahertz data. So to remind ourselves what we're looking at, here, B1H5A1, this is the future assembling brightest cluster galaxies, several interacting galaxies. We have an AGN here, another interacting galaxy, and here is actually another pair of interacting galaxies, one of which is an AGN, which don't show up very brightly in the radio. We already know that there is cool gas in the cluster through this Lyman alpha giant halo, and that is being powered by both the star formation in the cluster core and also these AGN. But the luminosity of the Lyman alpha halo is actually only a small fraction of the energy injection we expect from these galaxies, from the AGN and star formation outflows. So again, we can say, where is the rest of the energy going? Is it going into the ICM? So we model all of the galaxies in the field of view. So this is using HST catalogs, cluster members and non-cluster members, all of our ALMA sources. And when we subtract everything, this is what we have on the right-hand side. So we have lots of sources here, these that are labeled with R and in the yellow throughout the rest of the figures. And these are all at greater than 3.5 sigma significance. So we think, okay, what have we got? This is the image we saw before. This is overlaid on top of the HST image. And based on Xu and Jin's work, we find that there's a very low probability of them being noise fluctuations, both based on their signal to noise and also the number of independent beams in the image. And I think this is really reinforced by the fact that they do cluster around the cluster galaxies. There's definitely lots found near the BCG, the interacting galaxies, and the AGN. So there could really be a physical association there. We don't think they're undetected galaxies because based on their radio emission, if they were star forming, we would see them at 870 micron, which we don't. And similarly, when we stack 870 micron and HST data at all of the positions of the jets, we don't see anything at all come up in the images. So that tends to rule out things like tidal tails from interactions. That leaves us with the possibility of them being AGN jets or perhaps diffuse relics from previous cluster mergers. But as we've seen, these kind of diffuse relics are much more extended in scale And these are actually all unresolved in our data. They're really quite compact. So we think we have evidence here for multiple sites of radio jets in the cluster core, which is very exciting. And it's also quite different to what we see at low redshift, where AGN activity is often centered around a most massive central galaxy. To add another piece of evidence to this, we look at the radio infrared relationship. So this is the ratio here as a function of stellar mass. And for our cluster galaxies, thank you. For our cluster galaxies, we see that the relation is basically consistent with what is found by Del Vecchio et al. 2020 for the field. So they follow the far-infrared radio relation in this dense cluster the same as they would in the field. Our radio jets, on the other hand, they're an upper limit because they're not detected in the far-infrared, and they lie far below this relation. So again, it's really saying that this radio emission isn't coming from star formation. If we then put this all together, we can calculate the total power injected by the jets. So you might often use X-ray cavities to estimate jet power, although we don't see any in our relatively shallow X-ray data. But we can instead relate the power directly to the radio emission, bearing in mind the caveat that we only have an upper limit on the spectral index from our lower frequency data. What we find is that the power injected by the sum of the jets is at least 20% of the total energy injection into the ICM. So comparing with the injection from star formation and AGN outflows, and could even be up to as much as 100%, so the same amount. So it's a really significant addition into the energy ejection into the ICM. When we compare the position of the radio jets here in magenta with the residuals from the Ssaid modeling, we actually find that in yellow here, there's a positive residual after the subtraction of the Ssaid emission, which means there was an electron underdensity possibly at this point. And if that is linked to the jet emission, which would lower the electron density, that could be a really interesting result. So I think this is fairly speculative at the moment. We're trying to follow this up with more observations, but I think that could be a really interesting link between the two. I suspect my time is coming up, so I'll just finish by saying that we are hatching a bit of a master plan to try and study the cold ICM of the cluster, so the cold molecular ICM of the cluster using ALMA, using these kind of very bright background galaxies as backlights in absorption. So it relies on the observations, but I'd be very excited if we do get that. So I'll leave my summaries up. We've now detected X-ray and Ssaid emission from this hot ICM at redshift 2, and the galaxy removal was a really important part of that. We also think we've detected multiple radio jets in the cluster, which is very exciting, and it's a significant amount of energy injection into the ICM. So thank you very much, and I'll leave it there.